All right. Good morning, guys. Let me know if you guys have any questions that you want me to help you with. Joey, do you have anything? Yeah, I can go over any problems from worksheets 1 through 3, or the 10.1 and 10.6 additional worksheets from last week, or the handout from yesterday. Okay, root test problem. Okay, if I have a variable expression raised to the nth power, that's kind of like a giveaway that it's a lot easier to work with this if that n wasn't there, and so that's what the root test can handle. If I can take the nth root of this expression, and then just really just think about the limit as n approaches infinity of what's inside here. So the root test is always taking the nth root of whatever is in front of you. And the reason that we want to only want to do root test if I can raise everything to the n is it's supposed to be convenient, right? So if I can take the nth root of something all raised to the nth power, then all that can just go away. Focus on this portion here. Okay. And then the conditions for the root test is the same as conditions for the ratio test. So that means if this is less than 1, then it'll converge. If it's greater than 1, it'll diverge. If it's equal to 1, then it's inconclusive. But in this case, it's going to end up being 1/2 because we can just look at the ratio of the leading coefficients. And this is less than 1, so by root test, my series will converge. And again, it's variable raised to the nth power. If I have a numeric fraction raised to the nth power, then that's a geometric series test. Right? Morning. Okay, this is a little bit of a strange one here. This one ends up giving us inconclusive. But as a side note, I mean, this is not going to be on the test, but this is kind of like a more of a good thing to know is that 1 over n to the n is the same thing as e. That's the definition of e, and e is greater than 0. So by the nth term test, it can diverge. So this is kind of like a side note to know. I never went over it, but I'm not gonna suddenly put it on the test for us. But I think just this is something that's good to know. It may be useful on the AP exam. I may come back and put some of these things on a summary sheet for us. Okay, I'm just gonna pick out some problems here, unless you guys have specific questions.
I have a question. On the additional worksheet 1, could you go over part L?
Naomi, were you saying something? I didn't hear you. Maybe you can type it.
Okay, I'll type it.
Over part 1 on the first additional worksheet. So this one here, part 1. Like this worksheet 1 and 2 here from last week. Let me know which problem.
It was part L, not 1, sorry.
Sorry, I'm not able to hear you guys. I don't know why my sound's not working. Oh, L, okay. Okay, so sit right here, this one. 3 to the n minus 1 over n to the 2 to the n. The only L that I see, let me make sure that. Okay. So, let me write this out. Okay, so with this, I would feel like without that n there, it feels like it'll be easier to work on this using ratio test, sorry, geometric series test. But with that n there, it kind of makes things a little messy here. I would think about maybe ratio test because I see exponents. I don't see factorials, but I do see a bunch of exponents. And so I can jump into ratio test for this one here. So that's going to be a sub n plus 1 divided by a sub n. So that's going to be a sub n plus 1 means add 1 to every exponent. N minus 1 plus 1 will be n. This will be n plus 1. This will be 2 to the n plus 1 divided by the original series, which is the same thing as multiplying by the reciprocal. And now we can just try to move things around, clean some things up, and see what this gives us. So 3 to the n times 2 to the n times n, 2 to the n times 2 times 3 to the n times 3 to the negative 1 times n plus 1. Okay, I'm gonna clean some things up. I know that n over n plus 1 is just going to become 1 since n approaches infinity, so that's going to go away. This goes away. This goes away. So I have 2 times 3 to the negative 1 here. If I move that 3 up to the top, that's really the same thing as 3 to the negative 1, same thing as 3 to the first power above. So I have 3 over 2, and 3 over 2 is greater than 1. So the condition for ratio test is if my result is greater than 1, I can say that my series diverge. Okay, did that answer your question, Naomi? Let's see. Yeah. Okay, on the first page, I can try that one here. Okay, on that same page. Okay, so this seems like a kind of a messier problem here. It doesn't quite fit into any of the easy categories like p-series or geometric series. Nth term test would be inconclusive. So I'm thinking, well, what if we do limit comparison test? Because we can look at the numerator and denominator along with the square root and try to find a comparison partner. And really, I can just focus on this portion, right? I can just focus on the highest degree. I can strip away the coefficient. Just look at that degree relationship. So basically, it's going to be square root of n over n to the 5th, which is square root of 1 over n to the 4th, which is really 1 over n squared. And we know that, and the reason why we want to pick an easy comparison partner is because we should be able to find a series that we can quickly determine whether it converges or diverges. If we're picking a comparison partner that we have to do another test on and try to figure out if it converges or diverges, then it kind of defeats the purpose of finding a comparison partner. We want to find something that we can easily tell whether it converges or diverges. We can tell this is a p-series converging because, or converging p-series because my p is equal to 2. So I can take this and divide it by that. or I can multiply by its reciprocal. So by limit comparison test, I can say, let me see if there's no question. Okay. So in this case, by limit comparison test, if we divide the two series, we can prove that as n approaches infinity, that this is going to end up giving us a real number, and that real number will tell us that this series or this test is valid. And so therefore, we can say that these two series must share the same converging behavior. Okay, integral test problem, sure. So if something looks like a U substitution problem, I can kind of look at it and feel like, okay, if this is my U value, I can kind of get this to work out where it's integral of e to the U. Then typically that could be a good fit for integral test. But we need to confirm a couple of things here. N over e to the n squared, inconclusive by the nth term test, and it needs to be positive, continuous, and decreasing, which it is. As soon as we go from 1 to infinity, this is not going to break any of these rules here. So it meets each of our criteria for integral test. So now I'm going to take the integral. I'm going to use x, just feels more familiar here. I'm going to take and see if this gives me a real number. If it gives me a real number, then I know that this series will converge. But if this gives me infinity, then I know that this series is going to diverge. Use substitution. Okay, we know the integral of e to the u du is just going to be e to the u with a negative 1/2 in front. Okay, evaluate between 1 and b. Let me rewrite this. So as b approaches infinity, we know that infinity in the denominator is going to force the fraction to get really, really small and approach 0. So 0 plus 1/2e is going to be 1/2e. That's a real number. So we can say by the integral test, series converge.
I can make it real. Were you alone at any of them? I'm so sorry.
Well, no. Forget who was.
Jack was there.
Jack was at like 5 minutes then.
Jack's didn't be here this morning.
There's like 4 people up there.
He's online now.
Oh.
Okay, any other questions?
It's Raj.
Just looking at this one. I'm like, we go through. But you guys, you know, like it's 0 to.
Okay, what are the rules whether integral tests diverge or converge? So the way you can tell is if your limits approaches a real number, then your series will converge. If it approaches infinity, then your series will diverge.
Well, that's what I wrote down here.
I call it as parent as well.
No, I'm just getting that here. If functions and that's. And it converges like also because it's.
I do want to point something out here that if we want to review some of these, all these different tests and these rules, what we can do is in your packet, part 1, if you go to page, there's a couple of summary sheets I put in the back, but on page 58, we have the summary of all the infinite series. We can kind of go through these just to make sure that we're okay with each of these tests. So it's in your 10.1 and 10.6 packet here. The first thing is n-term test, right? If the limit as n approaches infinity of my rule sequence does not approach 0, then we can just automatically say our series will diverge. If it equals 0, it may or may not converge. It's not a strong enough argument. We have to look at another test. Oh, you mean, well, I think this may be a convenience thing. If you jump to another test, and if that other test works, you don't have to go through n-term test. But I'm just saying, n-term test usually is a good place to at least look at the problem and feel like, okay, is it going to not approach 0? If I can get through the problem with n-term test, then I can avoid a more complicated test. But you don't have to do it if you don't want to. But it's always a good option for your first test. Geometric series tests. If I have something that is I can see something like a constant ratio raised to the nth power, then that's usually, or if I can kind of if everything is multiplied in a way where I can move things around and get it into like a 2/3 or a fractional value raised to the nth power, that's usually a good indication that it's going to be a geometric series. And also, geometric series is the only one where I'm going to ask you what the sum is. So the sum of a converging geometric series is just going to be a sub 1 over 1 minus r. Okay, integral test, I said, if it looks like a U substitution problem, that typically is a good indication that we're going to be using integral test. And conditions, we have to make sure we state them. Positive, decreasing, continuous. If the integral converges, then the series will also converge. That means if it approaches a real number. If it goes to infinity, then our series will also diverge. Okay, P series, if I have 1 over n raised to the p power, it goes like 1 over right. If I can see that my p-value is in the denominator and it's a positive value, then it's going to diverge. But if I had like 1 over n to the -3, I shouldn't be using p-series test. I really should be bringing that n up to the top and proving that this diverges using nth term test. No, but remember p-series is only if p-value is positive, right? Yeah, if it's negative, it doesn't fulfill p-series condition. Yeah, it'll have to be p has to be between 0 or greater than 0 from 0 to infinity. Yeah. This will diverge, yeah.
Okay.
All right, if n is equal to 1, sorry, if a p is equal to 1, we have a diverging harmonic series.
We don't have to know telescope.
No telescope. Yeah. Okay, next up, alternating series test. Alternating series is if I have an alternator. And we know that with an alternating series, our condition for convergence is going to be less strict than without the alternating series. Or the alternator is going to make every other term negative. So it'll be easier for my series to converge. So normally, limit as n approaches infinity of a sub n. If we went through the nth term test and equal to 0, we normally have to say that it's inconclusive, right? That it doesn't it may converge, it may not converge. We don't know. But once we add an alternator to it, then this condition is good enough to say that the series converge. Okay. As well as a second condition, which is my a sub n plus 1 has to be less than a sub n. That's just to indicate that every subsequent term is decreasing. Right. It's decreasing, right? And I'm assuming that, yeah, you're right, because we can assume, we can, if we include the alternator in this, then everything kind of gets thrown off. But yeah, it's the absolute value of a sub n plus 1. But I was doing this without the alternator, but yeah, we can just put the absolute value to be safe. Right. But typically for us, this is only, we don't have to prove this. It's more like if we can show that, that's good. And then we just kind of state that second statement.
That would be wrong. Like with the second.
That is technically a condition, so we need to make sure we state it. Yeah.
Yeah, but like, you know,
I mean, I would say that, if it's multiple choice, I mean, we don't have to go through all that, but if it's free response, and they're asking for justification, then yeah, it's best to write those out. Connecting with alternating series test is the idea of absolute and conditional convergence. The idea there is that if my series can converge on its own without the alternator, then it's considered absolutely as convergent. It's an absolute convergence. However, if a series on its own diverges without the alternator, but all of a sudden can converge with the alternator, then we say that the series is conditionally convergent. An example of this would be an alternating harmonic series, because by itself, it would be diverging, P series, harmonic series, but with the alternator, it would all of a sudden converge because it would fulfill the two conditions that's required from alternating series. An absolute convergence would be something like 1 over n squared. Because if I remove the alternator, it would still converge.
Alternating. Say, since when it's absolutely convergent, can you just do P series? Because the alternator is not going to stop it from unless it is. Is there like functions that the alternator stops it from converging?
Nope, no. Yeah, so in this case, yes, you can use the P series. Well, I would accept it both ways, but I think alternating series, yeah, you're right. I think without the alternator, it will still converge. So I think P series is fine. Yeah.
is it just if it converges without the alternator, then it both converges and is absolutely convergent? Or are those two different things? Because there's like two different bullet points.
Oh wait, is one of them supposed to?
Because that one says if it converges, then it's absolutely.
I feel like one of them supposed to say diverges. I
No.
feel like.
No, because the you can only converge from this unless it doesn't meet the criteria, and then it's in.
Oh, I know, that's one thing I feel like the last.
Yeah, the last one should be diverge.
It is, okay.
Because it should say converge.
I was gonna say, there, yeah, that's why I was confused. If there's converges, it then converges.
Yeah,
If it
yeah.
Converges, then absolutely.
Thank you.
So I was just trying to trick you. You wanted to make sure you saw it.
I didn't.
Yeah, so if my series, if my positive version of my series diverges, then there's no way that if it fails the nth term test, there's no way that the alternator will bring it back from divergent. It needs to at least be in that gray area for this alternator to even have a chance to pull it into the converging realm.
Still want to test because it might be a 1 over n thing where it could converge. Right?
Say it again.
He says he wants to test it just to make
No,
sure
I
it's
said
conditionally.
we should converge because like the
Saying if
the
it
conditional, yeah.
If it fails that edge test, it's not gonna, like if it doesn't equal 0.
Oh, yeah, but,
Yeah, so for instance, if I have
okay, that makes sense.
-1 to the n times n over n plus 3, for instance, this one here. This one fails the nth term test because the limit of that does not equal to 0. And so it doesn't matter with that alternator there, it's still going to fail by the nth term test.
Okay, well, I've got a question about. It's like, there's like questions like that were just not. Okay, so it was like this, it's the square.
Okay, hold on, wait a second.
Oh,
Wait a
I'm
second.
sorry.
I'll make sure I can, I didn't miss something. Yeah, the bullet point, sorry, is incorrect. Oh, wait, the third bullet point. Oh, hold on, let me see. Doesn't 1 over n diverge even if it has absolute value? Yes, that's right. So 1 over n will diverge, but if it has the condition, if it has the alternator along with it, then it will be a converging series. So it's conditionally convergent because removing the alternator and including the alternator, they're producing different results. That's why it's called conditional convergence.
Of the review worksheet, finding the right test one,
Mhm.
why can't you just like this? I understand that the square root will thing, but like if you move the n down to like to make it 1 over n to the 4th and then square rooted it, isn't that just 1 over n squared?
Yeah.
So why do we need to go through LCT? I feel like you could just do it, you know what I'm saying? I'd be like,
Right, but
you know what I mean?
no, you're right, because the idea is that we go through limit comparison test or direct comparison test just to show that, you know, that the parent version of this would be comparable, right?
Cause I looked at like, when you got to the n, 1 over n to the squared, and I was confused on why you kept going.
Right, because this is, I mean, we know this is conversion, but even though this falls within the family, it's not a, we can make a stronger argument if we went through limit comparison test because we say, okay, this is, or direct comparison test to show that the idea is that, oh, that something that is within the family is still behaving the same way as the parent.
I know you explained this earlier, but I was writing down something on my test for letter K.
Yeah, this one here.
Or did,
I had it split across 2 different pages.
If you find the parent function of 1 over n squared, why do you multiply by n to the 4th over 1?
Oh, because I was still under the square roots. So it's still n squared. It's just, since this is in under square root, I didn't want to adjust all these powers. I just want to keep it the same. So I just kept the square root there. No, we haven't.
can we do ECT question, please?
Well, any LCT you can try going through DCT, but yeah, let me see if I can find one. I know DCT is not. That's a little bit harder.
No idea. Yeah.
You know, I want an example of what LCT is.
Okay.
You wanna,
What about? Go on.
it'll actually like keep going. No, but that's how you find these. You gotta like use it once it's too much.
All right, so this one here. Okay, so cosine of n over 2. If we think about how cosine is behaving, no matter if it goes to infinity, it's always going to, all right, cosine is always going to hover between -1 and 1. So, and so we know that's true, right? We know it's going to just hover between -1 and 1. Right? Then we're going to get larger or smaller than that. Now, n squared plus 4n, I can see that my parent function here, I can do this, I can do direct comparison, and the parent function, this is really just a 1. And then my denominator, my highest degree is n squared. That 4n is really irrelevant. So what if I do direct comparison test? with my comparison partner being 1 over n squared. So we know that 1 over n squared is converging p series. Okay. So let's see if this relationship holds, because if I have a converging series, then if I can show that this is less than my partner, then I know that this series must also converge. Let's see if this holds true. This is basically just a 1. Okay, so we just imagine that as being 1. Now my denominator is more than this. So my denominator is more than the denominator of the other fraction. That means this overall value must be smaller. So anything that's smaller than a known converging series must also converge.
Wait, but since cosine also. -1 change anything there? Like it was -1 over n squared?
I mean, it's still going to be less than 1 over n squared.
Okay. I just think.
Yeah.
Okay. See, my only issue is I don't know how, I would never think to do, -1 is less than cosine. Which is what it was.
Typically, I think I think this is always something good to know, that it's good to know about your visualizing your sine and cosine graph and just imagining, okay, no matter what value I put in for n, it's only going to hover between -1 and 1, unless I'm stretching it with a coefficient, or I'm adding, or I'm shifting it. But really, cosine and sine is just going to be a wave between -1 and 1. That'll be something that's good to know for our next half unit.
But not, not for the quiz. Or is it a test or a quiz?
The quiz.
But,
Okay, not for like the quiz.
I would have skipped 10 of that. Wait, this is a quiz, right?
quiz.
Okay, I would have skipped tennis practice. I would have skipped varsity practice for help sessions because of that. And God.
Okay, let me see if there's any other questions.
People start. Here's the issue. I think I'm good, and then the quiz comes. I realized I didn't know.
The DCT question.
Okay, the DCT, I'm just gonna save till the end. I'll figure that one out later.
I was gonna write some random crap in there. Be like, it looks like an around.
I'm just gonna look and be like, I'm sensing a 1 over n. That seems about exactly.
That's exactly what I'm gonna do. I'm just gonna guess.
No, because I'd probably like multiply with the other or something.
Yeah.
Just to like, find out.
Oh, that should be demon like if you put the n squared at the top. And instead of it being like this, I would cry. Like if it was n squared plus 4n over cosine n over 2, is that a function? Like
No, because then we can use nth term. And
Yeah, nth term test, which
and
is
then it's gonna be zero.
Yes. Oh my goodness. I probably wouldn't notice that.
yeah. Sometimes when you get too deep into
Uh-oh.
a test, sometimes we kind of step back and ask, wait, did we go through nth term test? Did we test the most obvious one? Because sometimes if it's too complicated, maybe it's supposed to be an easy problem where the nth term test can just handle it.
This actually the best one. But this one, I got one on me. Wow. That I don't understand how that's not like 1 over n to the 5.
It is, isn't it?
Yeah, no, it is. I'm just wondering why, like, this one feels like you have a strong argument with just the nth term instead of LCT.
Nth term would
Well, not
be 0.
P series. Sorry.
Yes, but I am comparing something with p series. But I mean, if something is within the p series family, we have to make sure. I mean, yeah, we kind of look at it and say this is probably going to converge because it's within the p series family. But that +5, we can't just say, oh, that's p series, because p series, that +5 kind of muddies the water a little bit.
Okay.
Does that make sense?
How's it both limit comparison and P series?
Okay. The p series is the comparison partner. 1 over n to the 5/3, which
Yeah,
is
there we go.
converging.
Okay.
And then if I can do, and this may not be a good fit for DCT, and so LCT is the good.
Advisement's gonna go crazy today.
I can't, I gotta go make up, or not make up, I gotta go do test corrections for AP physics.
Yeah, so LCT is really for something where you're like, wait, this looks like something that's within the same family.
But it's.
I'm pretty sure it's gonna converge, but let's do LCT so we can really show a strong argument for that.
Can you do LCP on these problems? Like, should there ever be a problem where you like that? Could you do LCP on that?
That's tough because that cosine kind of messes things up a little bit. But I think DCT is that's a little bit cleaner.
So just for the most part, I'm not gonna say this is like a rule, but like just, for the most part.
God, this fucking crazy.
If the function has, like a plus,
Yeah,
then most of the time it's gonna be comparison, right? Because I'm looking at the example, other than like,
right.
I don't-
But we should do nth term test first.
Oh, yeah.
Yeah, okay.
But just,
But after that,
if n term is inconclusive,
yeah,
then I should probably just go straight to.
right. Because when everything is multiplied, that should be a geometric series or it should be a ratio test. As soon as a plus or minus get involved in the expression, then yeah, LCT, nth term, root test, but root test is easy to spot.
If it's just,
Ratio test, root test is if there's n's in like the parentheses of a geometric, right? Basically,
Yeah, like,
because it's to the n power.
It's the nth power.
The entire thing's into the nth power.
Yeah, like this one.
Well, if there's no n's, and there's just 1 or 2, then that's geometric.
that's right. If there's no ends, it should be geometric,
I'm
right?
saying the entire, when I say the entire, function, I mean like, there's multiple, it's not just a fraction. Fraction and function are different.
Okay. And ratio test, I've only ever seen that when it's like an n and a something to the power of n. That's the only time when it's ratio, right? When something is to the power of n and it can't be.
Yeah, to the power of n and then factorials.
I think. I can't.
See, that makes sense. Makes sense. As long as it's not a negative 1 to the n, then I use ratio. Okay, or other than, root and geometric.
Yeah.
That's okay. Yeah, I feel confident, but then I'm not,
You should,
don't know.
You should feel confident.
you should.
No, I do feel confident. I already know I'm gonna get to the quiz and I'm gonna like forget that it's fucked up.
Well, that's bound to happen.
Or I'm gonna like work out an entire problem, but that would go wrong test.
Okay.
Or you can do this at the top of your page, like list out all the tests that you know, and then just and just go back to it and just like check things off. It's like, wait a second, did I test everything possible?
Yeah, I might do that, because I might also like, if it's less than 1, then it is.
Is there a blank back? Is there a blank back? Like, is it,
Yes,
four
yeah,
pages.
there'll be a blank.
there'll be a
back.
blank?
Yeah.
back? Thank you, Mr. Yang.
Okay.
Yeah.